So basically, it's using the U8G lib library, and then it's using the wire library for the I2C. And here's the constructor for the OLED display. This code could use some cleaning up. I think I'm only using one of these buffers here. In the setup, I'm not sure if this is even needed. I think that's to turn on one of the LEDs on the Arduino Pro Mini to show that it's booted up. Start the serial port just in case we need it. Let's start the I2C bus, device 9, and then we define the on-receive event callback. Excuse me. So we have a receive buffer here, and then a receive event index. So every time a byte is given on the I2C bus, it'll append it to this buffer here. Here's the ID. This stores what is configured using those dip switches. And then we have a complete buffer function. This basically means when it's gotten a command, it null terminates the end of the buffer and then resets it back to the beginning. And then we have the position. So this is the position of the rotary encoder. Some variables which aren't being used at the time. So here's the receive event, which is called whenever there's data on the I2C bus. And every time we're getting the ID, and yeah, this is bad coding practice here. I do need to clean this up. So we have this local ID and global ID. So we have data. We check to see what it is. If it's one of these letters, then it's a command. Otherwise, it is a data, so it's going to be a number, so we add it to the buffer. Some of these commands aren't used for this project. This is copy and paste code. What we're interested in is the position, so it's P. So we had a number, let's say the position is 123. So inside the buffer we'll have 123, and then when we get a P, we know that the data that's been queued in the buffer is the position. So we can complete the buffer, null terminate it, and then use this ATOI, which converts the character array into an integer, and then set that into the position. And this is kind of hacked together. I mean, not all of these are going to be position updates. This code needs to be cleaned up. I'll get around to that, but what we need to do is tell the OLED display library that we're going to start a new page. We set the font, set some font options. There's an offset, and then we write the position to the display. And then for some reason, in order for the I2C bus to receive events from the rotary encoder, we have to tell the I2C library to begin on device 9. My guess is embedded somewhere in this OLED display library, there's something that changes the what address the I2C bus is listening to. Some helper functions here. This basically prints something that you have to a buffer, very much like sprintf. It appears the Arduino libraries don't have sprintf. And then inside the loop, and this doesn't need to be done every time, it's just here for testing purposes, but it's basically reading the values of those dip switches and converting them into the ID. And then every time in the loop, it's going to update the OLED display, displaying that ID. And then once again, we have to set the I2C bus back to device 9. So that's the code, so that should give you an idea what happens. And as this project evolves, I'll clean this up and add more comments to it. In case I lost some footage, I'll just go over it again. So basically here I have this dip switch. So these switches are normally closed, normally open. So they're not like a tri-state where you can have floating negative or positive. So basically what I did was when it's normally open, there's these pull up or pull down resistors. It all depends if you put it on this side or that side of the breadboard. If it's on this side of the breadboard, the outermost pins are on the negative, and then if it's on this side of the breadboard, the outermost pins are on the positive. This isn't a complete short also, so when it's closed, oh wait, no, I take that back. Yeah, there's 4 resistors here to either pull it up or down. And then I made these LEDs here. So basically there's a red, which is supposed to indicate off or negative voltage, and then a green that indicates on or positive voltage. And then you can see that basically they're reversed from each other. So this one's, I think, the anode, and then this one right here is the cathode. And then they're tied to 2 current limiting resistors, and then they go to a common pin. So if you plug it in and there's nothing connected to it, both the lights are on. You can't see that very well, or you might be able to, but basically I should have used a larger resistor value for the green light. So right now it's that tri-state, so it's floating. If I connect it to negative, the red light turns on, and if I connect it to positive, the green light turns on. So here, because this one here is inverted, this one was meant to be the outermost rail goes to negative. So when it's on, it's really off in this case. And then these are connected to the digital pins 9, 8, 7, and 6, and code was written to display the ID that is currently being displayed here, or not displayed, set by the dip switches. And if you rotate the rotary encoders, it still updates the position here. So the idea here is that we can assign an ID to this display here, and it will only listen to rotary encoder updates provided that ID matches the ID that's set for the dip switches.